Swayam Prabha. Digital India. Educated India.
We get started with plug flow recycle reactors. Okay. Today, I will look at some illustrative examples just to say how these systems will behave. Okay. So, our system we have said earlier looks like this. You have a plug flow vessel here, it may contain a catalyst or it may have an inert through which your reactants are flowing, and there is a recycle. That recycle ratio is defined as Fa4 divided by Fa3. Okay. This is our recycle ratio. An example that of importance to us is use of autocatalytic reactions in mixed flow, because mixed flow is a form in which this context becomes. So, what I have got here is that a design equation for CSTR, where the reaction is occurring, where the rate function is given by CACB, and the reaction is A, it is autocatalytic. So, A giving B, but it is autocatalytic. Okay. Therefore, it depends on both A and B. Okay. Now, the point that I had wanted to get across to you is that when you look at this equation, you find that even if CB0 is 0, the size of the equipment is finite. The reasons it is not obvious from here. Why is it that even though you do not put CB0 in the feed, that the reactor gives you a finite result? Because you would expect that there should be CB0 in the feed. Okay. Now, we explained this. So, just explain this once again, just to put it in the context. To understand this, what we said is that let us look at the unsteady state. When you look at the unsteady state, what we have material balance for A, you have material balance for B, and this term which represents the reaction rate function, when you put CAI as 0 and CBI as finite, what we said is that as long as CAI, because CAI is coming in, therefore, the reaction rate is 0 at 0 time, but as time proceeds, since CA is coming in, this function becomes finite. As a result, what happens is that at steady state, there is the effect of CB which is there when you started up the equipment. So, what you are trying to say is that as long as material is there when you start the equipment, CSTR will always give you a finite result. So, that is, in other words, what we are saying is that CSTR is an instance of infinite amount of recycle. Therefore, the material that you have started at some time in the past history always lingers there, however small it may be. Okay. That is the point that we must remember. Now, suppose we look at the other example, which is a PFR, for example. There is no recycle, where you have material coming in, material going out. It is a PFR, okay, which means the recycle ratio is 0, and it has initially, let us say, certain amount of CAI, certain amount of CBI as an example. Let us see what happens. So, I have just written the unsteady state equation for a PFR, where del F del V is volume, reaction rate, and then this is the accumulation term. I have written for both component A and component B. Now, if you look at the what is happening to CA at 0, 0 means at the inlet at any time, it is means what is coming in is CA 0, similarly what is coming in is CB 0, and at any position inside at 0 time I have taken CAI and CBI. Or in other words, what we are saying is that we have a plug flow vessel which initially contains CAI, CBI, to which you start with CA 0 and CB 0. What happens to this process? What I am trying to say is that if CB 0 is 0, if CB 0 is 0, what will happen is that the reaction will proceed as long as there is some CBI, but this CBI will get knocked out after some time, and moment CBI gets knocked out, there is no further CB inside the process, and therefore, this rate function term will always be 0, and therefore, autocatalytic reaction in a PFR will not take off, because there is no CB. Whatever CB was there has been knocked out, and as soon as the CB is knocked out, the reaction stops. Okay. So, in a CSTR, autocatalytic reaction always goes forward, while in the case of a PFR, autocatalytic reaction does not move, because there is no product. With this, let us quickly look at one or two small examples to understand how the numbers look like. See, after all, finally, it is numbers that matter. This small exercise, what I have got here is that you have given data. There is some data which is given, which says there is a PFR in which this reaction A goes to B is taking place, and experimentally you find out that it gives you a conversion of 0.66. It is an experiment you have done, and you find that the conversion is 0.66. Now, you put a recycle pump and put it back. That means, the same reactor of volume V, this is also same volume V. Now, it is there is a recycle, the recycle ratio is given as 4. What is the likely extent of reaction or likely conversion you will expect? Now, of course, we know that when you recycle, your conversion suffers, because of the fact that it is a measure of mixing. So, how do you find out? To find out, which we recognize something that we said a little earlier in earlier classes, that if you have a plug flow device, the relationship between k tau p and x3, by x3 I mean x3 is this at the end of the reactor. Okay. So, this we have derived already. Okay. And similarly, if it is a recycled reactor, then this is the kind of relationship between residence time, rate constant, and recycle ratio. This also we have done earlier. So, what are we saying now? The same reactor you are using with a recycle of 4, which means what? Tau p equal to tau r. Same reactor you are using as a recycle, tau p equal to tau r. So, what it means is that in this exercise x a is given as 0.66, which means if you put x a means x3 is 0.66, you can find out k tau p, which if you plug in here, you will be able to find out the conversion. You understand? That means, essentially the data for a PFR is given, x3 is given. So, you know k tau p. Since the same reactor is used, k tau r is specified, therefore, you can find out the conversion. So, I have done this calculation, and the answers you get is not 0.66, but it is lower, which is what is to be expected. So, what is the message that we want to take from here is that when you recycle, you will find that you lose some amount of conversion, because the recycled actually is form of mixing, and mixing reduces the extent of reaction. There is another example which we have taken here. This I want to spend some time on this. So, what I have got here, you have a reactor, it is operating at 570 C. Most of this data is taken from an industry, okay, and it goes to a condenser. The reaction is A plus B going to C. Okay. And then it goes to a condenser, where the condensable gas, C is a condensable gas, which condenses. So, this is condensate. Okay. Now, you are putting a recycle, after the condensate you are putting a recycle, and then you heat it up, because the reactor is 570, the condensate, this condensate is operating at 45 C, the data is given. Okay. Therefore, you have to reheat it and put it back into the equipment. Now, this is a fairly common kind of device you will see in the process industry, that there is a reactor and the reaction does not go to completion. You try to recover whatever is useful to you, and whatever is not useful to you, you put it back into the process, something that we will do anyway, correct. So, data given is that the rate constant is given. By looking at the form of the rate function, rate constant, it is a second order reaction. So, it is k times C A C B is the rate function. Okay. So, rate function is k times C A C B, and this is 1 kilomole per hour. This I made a mistake, 1 kilomole per hour. Please make that correction, not 1, but 1 kilomole per hour. Okay. Vapor pressure of C is given as 0.2 atmospheres, and moles of A and B are equal. So, 1 kilomole per hour, sorry, 1 kilomole per hour. Reactors at 1 atmosphere, recycle ratio is 4. This all is given. Okay. because of this condensation, what is the effect you anticipate in the process? Suppose this condenser was not there, or if the condenser was there, it is an irreversible reaction. I am not saying it is reversible, it is an irreversible reaction. What is the effect that you would anticipate? Yes, product will go back, but this is not a reversible reaction. The reaction is not reversible. See, the rate function says k times CACB. Therefore, even if there is C present here, it does not affect the reaction. At least this is how it is formulated. So, the way it is formulated, it appears that it does not affect. Okay. I mean, is that right? I mean, would that make sense to you? What effect do we anticipate? To the extent that C is occupying part of the gas phase, the reaction what? This is now, let us to understand this. Just to understand this, I have done a small calculation. I want you to appreciate this. What I have done is I have written the stoichiometry. This is the stoichiometry. Okay. A and B are going in, they are all gases. A is a gas, B is a gas, and C is a condensable gas. Okay. It is a condensable gas. Is that clear? Okay. Now, what is the total moles? I have just added them all up. This is the total moles. R plus 1 F A 0, this is our convention. Our convention is that inside the recycle loop, we take R plus 1 F A 0 as our basis, R plus 1 x, R plus 1, and the product is R plus 1 F A 0 x. Okay. So, what I have done is at the incipient condensation, what is meant by incipient condensation? When the gas phase is saturated with C. So, at the incipient condensation, since the pressure is 1 atmospheres, the mole fractional component C in the gas phase must be given by this relationship, amount of C divided by the total moles. Yes or no? So, if you solve this, you find that excess is 0.33. What are we saying? At incipient condensation, the gas phase, the excess is 0.33. What does it mean? No, what we are saying is, till x becomes 0.33, there is no condensate. Till x becomes 0.33, there is no condensate. Your condenser has no, it does not perform any function, because till the gas is saturated, only after the gas is saturated, it will start condensing. Okay. So, this effect that x equal to 0.33, and therefore, to that gas phase, after its saturation only it starts condensing, will affect the gas flow that goes back to the reactor. How do we take that into account? To take that into account, what I have done is, before condensation what was the stoichiometry, after condensation what is the stoichiometry. Before condensation is what? Everything is in the gas phase, everything is in the gas phase. Okay. And after it started to condense, what will happen? The gas phase will have the excess, see, the amount of C in the gas phase is given by this relationship. Excess of that will condense. Is that clear? In the gas phase, so much material will be there, in excess of that will be condensed. So, therefore, what we will find is that the moles of F t that you will see going through the equipment is given by this. Is this correct, what I am saying? F t, R plus 1 F A 0 2 minus 2 x plus x s. This is what goes through the equipment. Is it all right? Now, notice what we have been trying to do. What we have been trying to do in this exercise is trying to set up a procedure for doing reactor design calculations for the situation where there is a condenser, when there is a condensate is taking place. Okay. And what we want to draw your attention is that in case of situations like this, we must first calculate what is the conditions under which the condensation begins, so that we can take appropriate decision regarding how to do the calculation. This is the exercise that we are trying to do. Okay. So, let us recognize that before condensation the total molar flow at the reactor exit is given by R plus 1 F A 0 2 minus of x. This is for x less than x s, and we showed that x is equal to 0.33. We have already shown that. Okay. Now, after condensation, we find that the excess, so F t is R plus 1 F A 0 2 minus of 2 x plus x s. Okay. This is after condensation, okay, where x s is 0.33. Moment we recognize this, all the rest becomes fairly straightforward. Okay. Now, what is volumetric flow V by V 0 after x? x greater than xs, because our interest is x equal to 0.5 and xs being equal to 0.33, our interest is x greater than xs. So, we know what is V by V naught from our gas law, we know it is F t by F t 0, T by T 0, P 0 by P, Z by Z 0. If it is an ideal gas, we know that this is 1, this is 1, this is 1. Therefore, F t becomes F a 0 r plus 1 F a 0 2 minus 2 x plus x s, and F t 0 we already given that it is a equimolar flow of A and B, where A is okay, and therefore, it is 2 F a 0. Now, therefore, V by V 0 is simply V by V 0 is F t by F t 0, we can put this as equal to what is already mentioned, the r plus 1 2 minus 2 x plus x divided by 2. What is C A? By definition F a by V. Therefore, we can substitute for F a, which is F r plus 1 F a 0 1 minus of x, and what is V? We already calculated V 0 times this whole thing. Okay. What is V 0? V by V 0 is this, that is therefore, we have substituted for V as V 0 times this whole thing, that is why we get this fairly simplified expression. So, what we have tried to do here is that, after all, any rate expression requires concentration in terms of conversion, and therefore, we have derived concentration in terms of conversion. We are now therefore in a position to substitute our rate function in terms of conversion, and we can integrate and find the reactor volume. Okay. So, what is the reactor volume? The reactor volume, if you want to calculate for a recycled reactor, we said dFA dV is RA is K Ca Cb, and we know what is Ca, what is Cb just now. So, we can substitute for all that, and therefore, we get an expression for the residence time in a recycled reactor in terms of all these variables. We can just simplify this and show that residence time is simply r plus 1 by K Ca 0 integral x1 to x2 of all these expressions. Notice here that x1, see our recycled reactor looks like this, okay, looks like this, why this is 0, this is 1, this is 2 and this is 3, and we have shown already that x1 is r by r plus 1 x2, same as r by r plus 1 x2, okay. We know we have shown all that, okay. Therefore, we can do this integration. I have put in all the numbers. A V 0 is what in this particular case 2 kilomoles per hour and so on. I have calculated the molar flow rate as so many cubic meters per hour, and concentration at the reactor inlet Ca 0 P by R T, okay, that comes out to be 3.6 10 minus 3 gram moles per liter. So, we know Ca 0, okay, and K value is given as 10 liters per gram mole per second. I will write here K equal to 10 liter per gram mole per second. So, K is also given, we can calculate all these numbers, and that is how I got this number as 23 seconds when K is equal to 10 liter per gram mole second. Okay. So, what have we done? What we have done is that for a recycled reactor, we have set up the rate expression, and then we substituted for Ca and Cb, and then replace this Fa as r plus 1 Fa 0 1 minus of x, and that is how we got the residence time by this expression. We have done this integration and found out the residence time to be 23 seconds, where x1 the lower limit is taken as r by r plus 1 x3, same as r by r plus 1 x2, where r value is given as r equal to 4, r equal to 4 is given in the problem statement. Okay. Now, that we have done the residence time, what is the reactor volume? Reactor volume is simply given as volumetric flow multiplied by the residence time. What is the volumetric flow? It is 138 cubic meters per hour. I have divided by 3600 to get in seconds. Okay. Cubic meters I have converted to liters, and then so many seconds. So, you get 900 liters per for the processing of 1 kilomole per hour. So, what we are trying to say here is that, just quickly recall what we have tried to do. What have we tried to do? What we have tried to do is, we have A going in at 1 kilomoles per hour, B going in at 1 kilomoles per hour into a reactor, where the second order reaction Ra equal to KCACB is taking place at 570 C, okay, and where rate constant is 10 liters per gram mole per second, where recycle ratio is R, and we want Xa equal to 0.5. Since this component A plus B equal to C, I will write here A plus B equal to C, okay, and since C is a condensable gas, you will find that the this exit here moment after condensation, you will find that this gas is always saturated with C. So, that effect is all that we have to take into account, so that we do the calculations as per procedure. Okay. This is what we have tried to do, and for the case of K equal to 10 liters per gram mole per second, we find for 1 kilomole per hour of flow, we find that you require a volume of 900 liters. So, in the recycled plug flow, what we have tried to demonstrate is that the basis that you have to choose is R plus 1 Fa0, number 1. Second point that we tried to say is that because of recycle, there is mixing inside the equipment, therefore, you lose on conversion. Okay. And therefore, you can use the recycled reactor device as a way of understanding what is the extent of mixing that takes place in the equipment. Okay. Third thing we said is that if it is an autocatalytic reaction, the recycles are required, otherwise the reaction does not go forward. But the fact that there is recycle and therefore, the reaction goes forward. If it is infinite recycle like that of a stirred tank, it might appear that you have not put any recycle in the feed, but actually because of the fact that there is so much of recycle internally, you do not have to put it continuously. These are the points that we have made in our presentation. So, now with this we will go on to our next topic, which we want to do is multiple reactions. Now, we have been writing our stoichiometry for single reactions. So, we want to write our stoichiometry. I just take an example where there are two reactions. We want to write our stoichiometry for the case of two reactions taking place. Okay. Now, there is a lot of material written here, but let me just run through this quickly. A reacts with B to give C and D, coefficients A, B, C, D given. Again, A reacts with C to form another product E. So, there are two reactions taking place. So, taking A as the basis, I have written here A plus B by A B, C by A C, D by A, and similarly A F by G, C equal to E by E. Okay. So, when you write this stoichiometry, which means what happens to all the species A, B, C, D, E and I and so on. So, these are the input values, all these are input values, okay. And these are the values at any instant where the conversions are whatever they are. So, what I have done is that since component A is reacting in reaction 1 and component A is reacting in reaction 2. Okay. So, I have taken let x 1 and x 2 be the fraction of A that reacts in 1 and 2. Okay. So, that is why I say that the amount of A that remains unreacted is the amount of A that you put in multiplied by 1 minus of x 1 minus of x 2. Okay. This is how we postulate what is happening. Once you do this, now what happens to B? B is reacting by this reaction, therefore, I have written what is the B unreacted is given by this. Similarly, the C is formed from reaction 1 and reaction 2. So, C is formed from reaction 1, C by A F A 0 x 1. Okay. C is consumed in reaction 2, therefore, I put a minus sign. D is formed in reaction 1, so D is D by A x 1. E is formed in reaction 2, therefore, F A 0 x 2. So, when we add up all this gives us F T 0. This gives us F T 0, okay. All right, this is F T, okay. And when you add up all this, you get F T 0 here, and then there are two terms, as you can see very clearly, F A 0 x 1, which is multiplied by the stoichiometric coefficients involved in reaction 1, F A 0 x 2, which is multiplied by the stoichiometric coefficients involved in reaction 2, where delta A 1 and delta A 2 is only what is written, is essentially stoichiometry that is written with respect to component A. So, the number of moles that you will see at any position in the equipment is what you start with multiplied by plus there are two terms, one due to reaction 1, one due to reaction 2. Moment you have done that, we recognize that we are able to now write what is the concentrations of species A, B, C, D in the equipment. Why is it required? It is required because our rate functions are always given in terms of concentrations. Therefore, we need to express concentrations in terms of variables that we can measure. Okay. So, CA is FA by V, we said is V by, this is gas law, this is something that we know, gas law. Okay. So, FT by FT 0, T by T 0, Z by Z 0, P 0 by P. Okay. Therefore, CA is what FA 0 multiplied by whatever is the amount of A that is remaining. The amount of A remaining is given by F A 0 1 minus of x 1 x 2. Okay. Therefore, and then V 0 is what V is V 0 times all these terms, which takes into account the effect of temperature, pressure and all that. So, this ratio essentially tells you how C A depends on x 1 and x 2. That is the most, once you can do for component A, you can do for any other component. So, we are able to express all the compositions A, B, C, D in terms of two unknowns x 1 and x 2. What is x 1 and what is x 2? To be able to find out x 1 and x 2, we go back and say how do you find out x 1 and x 2? You have to make two measurements. Any two measurements if you make either on A and B, that is enough to find out what is x 1 and x 2. Now, let us just look at this in some detail. Now, suppose we have a reaction like this, A goes to B and B goes to A. So, we write it as reaction 1 and reaction 2. So, and we write our design equation for a plug flow in this form, d by dV of F A is the rate of formation of component A, and component A is formed due to two reactions we say, which is reaction 1 plus and then reaction 2, where terms R 1 and R 2 are the intensive rates of the two reactions. What is meant by intensive rates? By intensive rates we mean that if you want to find out the rate of formation of a component, you multiply the intensive rate of that reaction by the appropriate stoichiometric coefficient. So, if there are two reactions 1 and 2, you multiply by appropriate stoichiometric coefficient to find the actual rate at which that particular component is formed. Okay. Therefore, dFA dV becomes R 2 minus of R 1, and it stands to reason because component A is formed from reaction 2 and it is consumed in reaction 1. Therefore, you get this. Okay. So, what we are now saying is that when there is a reaction like this, A goes to B and B goes to A, and we express this in the form of two algebraic equations, B minus A equal to 0 and A minus B equal to 0. Why do you say this is B minus A equal to 0? Our convention is products are positive coefficients and reactants have a negative stoichiometric coefficient. Therefore, we write the first reaction as B minus A equal to 0 and second reaction as A minus B equal to 0. When we express this in this matrix form, we find that the determinant of this matrix is 0, showing that the rank of this matrix is 1. So, what we are now saying is that if you have a set of algebraic equations as we have written down just now, you can find out number of those algebraic equations which are independent, or how many of these equations are independent, that will determine the number of reactions which are independent. That is what is being said. Moment we write this reaction A goes to B, B goes to A in this form, we find that rank of the coefficient matrix is 1, which means that there may be two rate processes, but there is only one independent reactions. What is meant by independent reaction? Which means that you need to make only one measurement, which is required to characterize the system given the initial state. If you know the initial state or the feed state, you need to make only one measurement, which that is what mean by there is rank is 1 or number of independent reactions is 1. So, what we are now want to do is that use this idea for a multiple reaction network like something like this. Okay. That means, you have a network which says alpha 1 1 A 1, alpha 1 2 A 2 up to alpha 1 equal to 0, like that there are p reactions. Notice here the first subscript is reaction, the second subscript is species. So, when we say alpha 1 1 first reaction, first species, alpha 1 2 is first reaction, second species. This is the nomenclature of writing a network of reactions. Okay. Now, when we express this in the form of a what we call as the stoichiometric matrix, which is alpha 1 1 1 to alpha 1 n, alpha p 1 to alpha p n. So, this matrix is the stoichiometric matrix. This matrix determines what happens to these reactions. Therefore, the rank of this matrix will tell you how many reactions are independent. Okay. The rank will tell you how many of these reactions are. So, if the rank is R, what does it mean? That in this network, if you want to understand the composition of the system at any instant of time after beginning, then you only have to make R measurements. So, if you have R measurements, the entire n component system can be fully specified. This is all is meant by the rank of this matrix. Having said this, so what is it that we can learn from this? What we can learn from this is that if there is a component j, if you have a component j, therefore, A j minus of A j 0 represents the change in this component j. How can this change come about? This change comes about because there are R independent reactions, Okay. And there is a contribution to this component J's change because of each of these independent reactions. Is that clear what we are saying? Delta 1 j is the change in A j because of reaction 1, delta 2 j is change due to reaction 2, similarly, delta R j is the change due to reaction R. Okay. Now, we recognize that this term delta 1 j by alpha 1 j, what does this mean? Delta 1 j by alpha 1 j, the change in component j in due to reaction 1, alpha 1 j is the stoichiometric coefficient of component j in reaction 1. This is change due to reaction 1, this is the stoichiometric coefficient. Similarly, delta 1 n divided by alpha 1 n, what is it? It is a change in component n due to reaction 1, and alpha 1 n is the stoichiometric coefficient of component n due to reaction 1. So, this ratio by definition is constant, because this belongs to reaction 1, therefore, this is equal to beta. Is this clear? Change due to reaction 1 component j divided by the stoichiometric coefficient of component j in reaction 1, that is a constant, okay, that we call as beta, beta 1. Similarly, for reaction 2, similarly for reaction R. So, what is beta 1, beta 2 and beta R? These are change, essentially this is what are the units of this? Moles, change is moles. So, with this relationship we recognize that this whole change A j minus of A j 0 can now be written like this. We have written what we have written is that this delta 1 j, okay, we can write it as delta 1 j is beta 1 times alpha 1 j. Okay. So, delta 1 j is beta 1 times alpha 1 j, delta 2 j is beta 2 times alpha 2 j. Similarly, delta R j is beta R times alpha R j. Okay. So, we are now able to express the change in component j in terms of what we call as the molar extent of reaction multiplied by the appropriate stoichiometric coefficients. Now, it is customary for all of us to always talk about reactions with respect to a reference. We always find it convenient, because we are used to saying that the conversion is 50%, 40%, 80% and so on. So, if you have a reference, it is much easier to comprehend what is going on. Therefore, if you have a reference component A 1 0 with respect to which you want to understand the change in A j, then you can divide throughout by A 1 0. So, that now this term beta 1 by, now this refers to change with respect to a reference species. There is an advantage in keeping a reference species, because with respect to that reference frequently our numbers can be made to go to 1, because it is if you choose the reference appropriately, otherwise it will not go to 1. Okay. Therefore, by looking at a reference component A j minus of A j 0, we are able to write in this form x 1 alpha 1 j, x 2 alpha 2 j up to x r alpha r j. So, what is it that we have done? By an appropriate definition, we are able to express the change in A j minus A j 0 in terms with respect to A 1 0 in terms of x 1 alpha 1 j, x 2 alpha 2 j, x r alpha r j. There are independent values of x 1s, x 1 to x r. So, what does it say here? That in a network we have to choose a set. See, after all, we have a network. So, the rank is R, which means what? You have to choose from here a set or some reactions, say maybe 1 2 3 1 2 4 whatever. So, that particular set that you have chosen must have a rank R, it should not be different. So, the set you choose must be a complete set, that is important. So, if you chosen the right kind of set, so that the rank is R, okay, then you find that the kind of relationship that we have set up works nicely for you. Change in A j is given by x 1 to x r multiplied by the stoichiometric coefficients. Okay. See, in this very important question, the number of rate processes are p. The rate processes, there are p rate processes. Okay. If you recall, I mentioned this a little earlier. How many rate processes are here? There are 2 rate processes. There is only one independent reaction. Similarly, in a network you can have p rate processes, but rank can be R and R is less than p. delta 1 j by alpha 1 j. What is meant by delta 1 j by alpha 1 j? Let us just look at that once. No, I'll just. What is delta 1 j? It is change in component j due to reaction 1. Change in component j due to reaction 1. You are dividing that by alpha 1 j, the stoichiometric coefficient of component j in reaction 1. So, this ratio is something unique to the reaction, which is reaction 1. So, therefore, it must be equal for every component that participates in that reaction. That is why I have written delta 1 k divided by alpha 1 k. Every component that participates in the reaction, this ratio is fixed.
So, number of betas will be p numbers.
Number of? The number of reactions may be p, but the number of independent reactions are r, and you need to take only r reactions to understand the system, because you do not need p measurements, you need only r measurements. R is less than p. In other words, what we are saying is that when there are two reactions, see examples are here, when there are two reactions, we need only one measurement that is sufficient to characterize this system. The reason is the independent reactions are only one.
So, in this case R is an independent number of reactions.
R is the number of
P
independent,
is the
total number of reactions.
So, which reactions are independent?
That is the now there is a procedure for finding out. When you do matrix elimination, you have done in your school, I am sure, you have to do a matrix elimination, and the elimination procedure will tell you which are the reactions they are independent. Because that will tell you, by looking at that itself, it will tell you the reaction 1, 2, 3 are independent, 2, 4, 5 are independent. The elimination procedure that may have been taught to you in, otherwise we can talk about it, but it is not a very difficult thing. So, is this point clear? What we are saying, when you have a network of reactions, there are r independent reactions, okay, and then these are independent reactions x 1 to x r, and therefore, you need only r measurements, and therefore, if you want to find out change in any component with respect to a reference, this becomes what we have written here x 1 to x r multiplied by the appropriate stoichiometric coefficients. Now, advantage of this technique is that given species j, we are able to write the species j in terms of the x's x 1 to x r. Therefore, it makes the network easier to deal with, otherwise it is a little bit complicated. Okay. So, let us just illustrate this by an example. We will illustrate this by this example. We have chlorination of benzene. Okay. What do we have? We have chlorination of benzene. Okay. So, you have benzene reacts with chlorine to give monochlorobenzene, it gives you HCl. Benzene monochlorobenzene reacts with chlorine to give you dichlorobenzene, dichloro with give you trichlorobenzene. Is it okay? So, you have component C is component 1, B is component 2, MB is component 3 and so on, all the components are listed. Okay. Now, the question that we have to address is, how do you write the stoichiometric table for this multiple reaction? We want to write the stoichiometric table and hence express concentration of all the relevant species in terms of conversion which we can measure. Okay. How do we do this? So, what is done here is that you have written the material balance A j minus A j 0 by A 1 0 equal to x 1, just recall our equation here, just A j minus A j 0 is x 1 alpha 1 j, x 2 alpha 2 j up to x r alpha r. How many independent reactions are here? We can say it is 3, because we are familiar with chlorination, we are saying it is 3, but it may happen that you may have to determine the rank to be sure. In situations which you are not very clear, you may have to determine the rank. Okay. In this particular case, we know the answer, therefore, we have not done. See, the procedure for determination of rank, there is a Gauss elimination method is there. Yeah, you have to make all the diagonals 1 and below the diagonal 0, and you have to count the number of diagonals which are 1. So, it will be number of components is 6. There are 6 components, there are 4 reactions, therefore, there are 4 1 2 3 4 and then 6 reactions. So, it will be 3 rows and 6 columns, 3 rows and 3 rows. Okay. Is that okay now? We go forward. So, what we are saying is that we can write our stoichiometry this form, that means A 2 minus of A 2 0. I have taken A 2 minus of A 2 0 as an example. This is given as x 1 alpha 1 2, x 2 alpha 2 2, x 3 alpha 3 3. Is this clear what we are saying? So, what is the value of alpha 1 2? That means, value of alpha in reaction 1 component 2, reaction 1 component 2, what is the value of x? Alpha is minus 1. What is alpha 2 2? Reaction 2 component 2, reaction 2 component 2 0. Now, alpha 3 3 x 3, what is x 3? It is not mentioned here, x 3. So, what is the value of component 2 in reaction 3? 0. So, therefore, it is minus of x 1. So, similarly, you do for component 5, you can do for all the components. I have just taken only 3 components because it is convenient. So, reaction 2, if you have A 5 minus of A 5 0 divided by A 1 0, what is it? X 1 alpha 1 5, x 2 alpha 2 5, x 3 alpha 3 5. What is x alpha 1 5? 0. Alpha 2 5? 0. Alpha 3 5? Okay. What is plus 1? Plus 1. Okay. Now, if you want to do this for A 3 minus of A 0, A 3 is what? That is, so it is x 1 alpha 1 3, x 2 alpha 2, x alpha 3 3. So, what are the values? X 1 minus of x 2. Or in other words, based on our stoichiometry, we are able to express these species in terms of our unknowns x 1 and x 2. This is the important point. So, what it says is that if you take, what is our reference? Chlorine is our reference, na? Okay. Chlorine is our reference. Suppose you take benzene as reference, no harm is done, no harm is done. So, what we have done here, A 2 minus A 2 0 is x 1 alpha 1 2 and x 2 alpha 2 2, x 3 alpha 3 2. Is that clear? So, what we are able to now do is that express A 2, A 5 and A 3 in terms of x 1 to x 3 multiplying by the appropriate stoichiometric coefficients. Now, let us illustrate one more problem. So, what we have tried to do here is that if you have a multiple reaction, you must be able to express your results using the standard procedure. Okay, that is the most important. Now, this is Q 2 where we want to set up the stoichiometry and then see whether we can set up the equations that are required to describe the process at work. How do we do this? When you get a monster like this, you should first find the number of independent reactions. How do you find the number of independent reactions? We said you have to make zeros along the diagonal by row manipulation, and if that is the case, the rank is the number of independent reactions you can see below the diagonal. Okay. So, I have set up this matrix for this, which looks like this: ammonia, oxygen, nitrous oxide, water, and then NO2 and nitrogen. Okay. So, how did I get this? I got this by putting the appropriate stoichiometric coefficients here. If you put minus 4 means it will be minus 4 there itself. Okay. Now, let us just look at these reactions. So, reaction 1 gives you NO, reaction 2 produces nitrogen, reaction 3 produces nitrite, reaction 4 produces, what does it produce? Reaction 4? Ammonia, 6 NO gives 5 H2, is balanced, is it? 10, okay, seems all right. Okay, okay. Now, please recognize that there are some reactions which throw out nitrogen away into the atmosphere. This reaction is also there, this reaction is also postulated to throw into the atmosphere. So, this 4 NH3 plus 3 O2, there is nitrogen gas produced, similar to what we talked about anammox and so on at an earlier stage. Okay. Now, what I want to do is, I want to see, after all, if you want to do a design or if you want to do a kinetic measurement, you need to be able to relate what your collection to the equipment which you have done the experiment with. So, you have to generalize your result so that people can use it. So, keeping that in mind, what we have done is, we have written the stoichiometry for A1, A5 and A6. Okay. All these sets of equations, for example, what is it that I have written? Based on this, the rate at which A1 changes with respect to volume is given by minus 4 R1, minus 4 R2, minus 4 R4. Is it correct? Can you please tell me? d by dv of A1, is it correct? Can you just check and tell me? A1, d by dv, A2, A5 and A6. Tell me if it is okay. How do we check this? In our material balance, the left hand side is about what happens to our measurement. The right hand side is what happens to the reaction. So, the left hand side is d by dV of A1, therefore, we can replace that from our stoichiometric table. Our right hand side are the rate processes. So, if I ask you which are the rate processes in which A1 is involved, A1 is what? According to us, A1 is ammonia. So, where are the ammonia is involved in reaction 1, reaction 2, reaction 3, so reaction 4. So, you can say reaction 1 is minus 4, reaction 2 is minus 4, reaction 4 is also minus 4. So, the stoichiometric coefficient of ammonia is minus 4. The reason it's minus 4 is because it is a reactant. So, similarly, we have written for other species. I have chosen A1, 5 and 6 because I get some neat results, because our the results are very neat in the sense that it gives simple answers. That is why I have taken it like that. Okay. So, I have done this here, please see if it is okay. A1, A5 and A6 gives us, A5 gives you x3, A6 gives you x2, and A1 using these two you can eliminate x2, you can get x1. So, what we are able to do using the stoichiometry is that we are able to express our left hand side in terms of x1, x2 and x3. A1 depends upon x1, x2, A5 depends upon x3 and A6 depends upon x2. So, the left hand side you are able to replace in terms of x1 and x2 and x3. What is the right hand side? These are rate functions R1, R2, R3, R4, R5, R6. We know that the rate functions depend upon concentrations. We know how to express concentration in terms of conversion. In this case, in terms of x1 to xr. So, the right hand side we know how to express in terms of x1 to xr. The left hand side also we know how to express in terms of x1 to xr. Therefore, you get a number of differential equations in x1 to xr. On the right hand side is a very nonlinear function of x1 to xr, but at v equal to 0, x1 equal to 0, xr equal to 0. Therefore, it is an initial value problem where the initial state is specified. Therefore, you can forward integrate and get your results. So, when the final result looks something like this, I have done the manipulation. What it finds is that dx1 by dv looks like this, dx2 by dv looks like this, dx3 by dv looks like this, where the right hand side is a function of x1, x2, x3 and temperature. So, these functions, how do you find out these functions? These functions come from an understanding of the rate process R1 to R6, for which data will be available to you. Okay. This should come from an independent set of measurements that some people would have done. So, that the left hand side x1 to xr is related to these functionalities, which is known to you. Therefore, you can integrate forward and then determine what happens to x1 as a function of volume, x2 as a function of volume, x3 as a function of volume. Essentially, what returns to you from this integration are these results, and this is what we want in a design or simulation or in a control problem. This is what we want. We want to tell what happens to x1, x2 and xr as we change our system. Okay. I will stop there.